Okay, you're good.
Okay, and you've admitted everybody in the lobby?
Mm-hmm.
Okay, excellent. Hey, greetings all. Welcome to this Tech Talk today, and we're really honored and privileged to have as our guest speaker Professor Steven Frankel from Tech9. And you know, it goes without saying that Professor Frankel has an amazing background and is one of the renowned authorities in computational sciences. And in particular, he has been one of the few people who have bridged between our world of simulation methods and this exciting new emerging area of quantum computing. So he very kindly agreed to share his knowledge and some of his observations in this field with us. I'm not going to eat up his valuable podium time with a long introduction, but Professor Frankel has had a very illustrious career. He is, of course, holding a chaired position at this prestigious Israel Institute of Technology, Tech9, that all of you know about and look up to. But you know, before that, Professor Frankel was at Purdue University. He has you know, a long career there. He finished all his graduate work. I would say, I mean, his PhD work at State University in Buffalo, New York, where he worked with Professor Givey, who you know, many of you in the mechanical engineering space also know. And he's had a very unique experience and career building progressively on the academic side, but also working with industry. He works with a lot of aerospace and defense, but he's also worked with hardware providers in the high-performance computing arena. And he also, if I remember right, Professor Frankel, you worked as part of your sabbatical, you worked at a quantum computing organization, I think Quantum Machines, right? So. He leads a big group at Tech9, and you know, ANSYS and Tech9 through Professor Frankel are hoping to work closer and closer together in the future. So without further ado, I'm going to turn it over to Professor Frankel. Thank you.
Thank you very much, Dipankar, and thank you for everybody for attending. The title of the presentation today is Quantum Computing for Computational Fluid Dynamics. And the subtitle for some reason disappeared here, but it's beyond the hype, basically, because there's a lot of hype in this field, and I want to basically stay true to what's possible at the moment. There's the beyond the hype. It took a second to show up. Okay, so before we start, I wanted to start with a thank you and a gratitude to Dipankar and Prith and ANSYS, everybody ANSYS, for helping to sponsor my CFD Impact Conference that I run every year here in Israel. And this year it was our first time back since COVID, and it was a big success. And it was no small part due to ANSYS's support and local ANSYS Israel having a booth. You can see Dvir and his colleague there working with visitors to the booth. And he also gave a talk on the exciting new GPU capabilities of ANSYS Fluent. So thank you very much for your support there. So this is the outline of the presentation today. And it'll start with a quantum computing crash course, and we know the problems with crash courses is that they crash. But we'll try and cover a semester's worth of material in a few slides just to get you familiar with some of the terminology and you know, technical details of the field. And then we'll catch you up on the latest, greatest algorithms in the space in a more general sense, and these are called variational quantum algorithms. We've made a small contribution to that field in the last year or so, which I'll talk about, something called PONSATs. And then we'll move into the second half of the talk, which is the quantum CFD. We'll talk a little bit about the general approaches there, and then we'll zoom in on two specific sort of options to realize the potential of quantum computing for CFD. One is a more traditional linear system solver-based approach, like AX equals B, and then another is we're looking at quantum lattice Boltzmann, along with other people in the field are looking at the same technique. So this is the scope of the talk. And before I start, because we have CFD experts in the room and we are a CFD lab, as Dipankar mentioned, it's actually now the 30th, I just realized today, the 30th anniversary of the CFD lab. I was 20 years at Purdue University after my PhD. and then the last 10 years at the Technion. And these are some animations and stills from some of our recent work at the Technion. And our theme over the last 5 or 6 years has been basically trying to enable high fidelity coarse grid simulations of challenging problems in CFD, particularly high-speed flows, hypersonic boundary layer transition, scramjet combustion, and the enabling factor has been twofold here. One has been the GPU, and we've switched over to all GPU in the last few years, and it's made a huge difference for us. And combine that with really world-class, in my opinion, numerical methods that my students have developed. It's enabled us to do simulations on the order of tens of millions of grid points, and compared to simulations that are done at hundreds and thousands of millions of grid points, with different approaches. So these are just some of the recent simulations. And then of course, we've done some more conventional CFD with high fidelity tools, like these urban canopy flows, which you see on the right, and some rotor noise simulations and some supersonic jet noise simulations that are producing some very interesting results. But this has all been enabled by our numerical methods and the GPU. And if you're interested in some of the details on this, because that's not the focus of the talk, nor am I prepared to get into all the details right now, we've been fortunate in the last year or two to publish at least 6 papers, I counted, in journals that are detailed documentation of all our numerical algorithms. And we've even heard from people in other countries who've actually implemented what we wrote about and are getting similar results. So these are something that you can take a look at, and I'll share my slides with Dipankar to distribute to you after the talk. So this is the traditional part of the CFD presentation. Okay. With that, let's dive right into a quantum computing crash course, right? So we know that the fundamental unit of classical computation is the bit, and the bit can be in a state of either 0 or 1. It's usually realized in a transistor, and current flowing through a wire would be considered 1, and when there's no current flowing through the wire, that would be considered 0. The quantum equivalent of the bit is called the quantum bit, or the qubit for short. And just like the classical bit, it can be in a state of 0 and 1. But unlike the classical bit, because it follows the laws of quantum mechanics, it can also be in a superposition of the 0 and the 1 state at the same time. And this allows you to basically do quantum parallelism, because for a single qubit, you can actually evaluate, let's say, a function at multiple inputs at the same time. So this is part of where the quantum superpowers come from. In addition, if you have more than one qubit, you can so-called entangle them by doing something mechanically to them, shining a laser on them or whatever, and you can entangle these 2 qubits such that if I take one of the 2 entangled qubits and I move it to the other side of the planet and I do something to one of the qubits, the other qubit is instantly affected by that. It has this strange spooky action at a distance, as Einstein referred to it. And so this, again, superposition and entanglement are 2 of the sort of quantum computing superpowers that we don't fully understand, but we can definitely try and exploit for computational advantage. Now, qubits can be realized in a number of different ways. You basically need any 2-level quantum mechanics system. So some classical examples would be electrons in the spin up or spin down state, the horizontal or vertical polarization of light, or the ground state or the excited state of an electron in a molecule or an atom. When it comes to building these qubits, these are some of the modalities shown here in the lower left that are currently being explored, with the 2 most prominent being superconducting circuits, which are primarily used by Google and IBM, and trapped ions, which are primarily used by Quantinium, which used to be Honeywell, and IonQ, which is another promising company in the space. And these computers don't look like laptops or desktops. These are a couple of pictures of superconducting qubit-based quantum computers and a trapped ion-based quantum computer. And what you see here is really the trappings of a dilution refrigerator, because these qubits have to be, in the context of superconducting qubits, cooled to temperatures colder than outer space in order to minimize disturbances, noise from the environment. And so the chip itself sits somewhere in the bottom of this monstrosity, and everything else is to deliver signals and to keep the chip cool. And over here, it looks like basically a typical optical table that you'd see in an optics lab with a lot of mirrors and lasers. to actually trap the ions and manipulate them as part of the computation. So again, these are not laptops or desktops at the moment. Now, one of the advantages of quantum computing is the large computational space that you have available to you. And Chris Monroe, who was originally the founder of IonQ, has this quote here: every time you add a qubit, you double your possible outcomes. So if you have 20 qubits, just 20 qubits, there are 1 million possible outcomes, 2 to the 20. If you have 100 qubits, you have more possibilities than there are bits in all the hard drives in the world. And with 300 qubits, that's more possibilities than there are particles in the universe. So the dimensional space where these computations live is very large, and you can imagine that translating into a very fine grid direct numerical simulation of turbulence, should you be able to somehow harness that computational capability. And to help you appreciate or understand this a little better, it's common to show analogies of the bit and the qubit. So the bit would be like a typical light switch with an on-off button, the 0 and 1 state. And a qubit could be analogous to a dimming switch for a light, where you can have on or off, or somewhere in between, or somewhere combining both on and off, as the case may be. Another typical example that I like is a coin. If you take a regular coin, it's either heads or tails. But when you flip it up in the air and it's spinning, as it's spinning, you can think of it as being simultaneously in both heads and tails. And it's only when it lands on your arm and you make a measurement, that you get either the 0 or the 1 state. So this is an analogy to the qubit construct, basically. Okay, so now let's get a little bit of mathematical here. So we said that bits are the classical computing units, which are 0 and 1. And if it's 0 and you check it, you measure it, so to speak, you're going to get 0 with probability 1, right? If it's a 1, if it's in the on state, if the current is flowing, and you check it, you measure it, you're going to get probability 1. But a qubit, as we said, in general, a single qubit can be in a state of both 0 and 1, and I'll explain this notation in just a minute. And when you make a measurement, you check what state the qubit is in. Because of the laws of quantum mechanics, they say you collapsed the wave function, so to speak, which governs the underlying behavior of the quantum state, and you'll get 0 with probability magnitude of alpha squared, and you'll get 1 with probability magnitude beta squared. So alpha and beta are called the probability amplitudes of the quantum state, and by the laws of probability, the magnitudes have to sum to 1. These are complex numbers by the laws of quantum mechanics, and this is how we mathematically represent the quantum state as a two-dimensional complex vector. The notation that you're seeing here with the vertical line and the angle bracket is called bracket notation. It was invented by Paul Dirac, one of the founders of quantum mechanics. And it's just basically, whenever you see something like this, you should think of it as a vector, which we typically represent with arrows or boldface, depending on the typography. And it's a column vector, okay? And the 0 and the 1 states that we see here are represented as the so-called computational basis states, which are the column vector 1, 0 for the 0 state and the column vector 0, 1 for the 1 state. We can also represent qubit states visually. Even though we have a two-dimensional complex vector, you'd think we need 4 numbers to represent it, right? A real and imaginary for both alpha and beta. But by cleverly taking advantage of spherical coordinates, Felix Bloch, came up with the Bloch-sphere parameterization or visualization of the qubit. So we can think of a qubit as a vector centered at the 0, the origin of the sphere, and then touching the surface of the unit sphere, again, because the magnitude has to be 1. And it can be described by its polar and azimuthal angles. So only 2 numbers can be used to describe the qubit in this representation. And this is great for single qubits. If you have multiple qubits, it doesn't work, but for single qubits, it's a very nice way to visualize. And here are some other examples. Again, this is the general superposition for a quantum state psi. This would be a ket vector. The sum of the 0, 1. And here's another one, phi, which is got 2 different amplitudes, gamma and beta. And then once you have these bras and these kets, once you have these kets, you can actually form bras, which are complex conjugate transpose of the kets, and those are written in this notation shown here, which is with the angle bracket on the left and the vertical line on the right. And they're defined as as I said, the complex conjugate transpose of the ket. Once you have kets and bras, you can form brackets, and that's where the notation or the name of the notation comes into play. You can form a traditional inner product or a dot product or the overlap of two vectors, as we know about it from our CFD background, by putting the bra and the ket next to each other. And oftentimes we write it as a shorthand, just putting it psi and phi in terms of the angle brackets. We can also form outer products, which produce matrices, and we can form tensor products, which are useful to represent multiple qubit states. And some examples of those are shown below. Here's an inner product of two quantum states, and you can actually form the inner product and get the overlap of the two states, so to speak, the dot product of the two states. Here's an outer product where you can see the formation of a matrix, which becomes an operator, which we're going to talk about in just a minute. And then finally, if we have multiple qubit state, we use the tensor product. And so here's the tensor product of 3 qubits. One in the 1 state, one in the 0, and another in the 1 state. And when you carry out the tensor products, you get 8 numbers. And this is an example of how with 3 qubits, we have 2 to the 3 numbers that we can compute with. So with just 3 qubits, we have 2 to the n numbers, so we have 8 numbers. So if you have 100 qubits, 2 to the 100 is a pretty big number. Okay. Now, what do we do once we have these qubits? We can represent them we can build them, we can represent them mathematically, we can represent them graphically with the block sphere. How do we do quantum computation? So first of all, once we have this quantum state, we can actually change the quantum state by applying what are called quantum gates. And they're called gates in analogy with classical computing and classical gates. And they take the form mathematically of matrix vector products with a unitary matrix, and this is as a result of the laws of probability and quantum mechanics, where we want to preserve the norm of the vector when we apply a matrix operator to it. And here's a table showing you some of the traditional single and 2 qubit and 3 qubit gates. So here's a identity gate, which is this is what it looks like in terms of the get operators and the bra operators. Here's the matrix. And when you apply the identity operator to the 0 state, you just get the 0 state. When you apply it to the 1 state, you just get the 1 state. And in the quantum circuits that we're going to be describing in a minute, the notation, it looks something like this with a box and an eye in it. The X gate, which is also a classical gate, when applied to the 0 state, flips the state of the qubit to the 1 state, and applied to the 1 state would flip it to the 0 state. And pictorially, in the circuit notation, it looks something like this with an X in it. And then the Hadamard gate is really cool. The Hadamard gate looks something like this, and this is the matrix operator. And when you apply it to the 0 state, it produces a equal superposition of the 0 and 1 state. And you apply it to the 1 state, you get a similar superposition with a phase difference here with a minus sign. And it looks like this in the circuit representation. So the Hadamard gate is commonly used to put qubits into superposition states prior to doing some computation to take advantage of that state. Here's a C0 gate, which is a 2 qubit gate, where you change the state of the first qubit depending on the state of the second qubit, and that is depicted with 2 wires here for the 2 different qubits, and the not symbol here with which is actually here, and this is the control qubits. You have the control qubit and the target qubit, and you can extend this to 3 qubit gates and more. Here are some pictures with the block sphere. Again, this one on the left is just showing the 0 state and the 1 state on the block sphere as the north and south pole, and then a superposition state would be somewhere else on the surface of the sphere. So if you applied, for example, an X state to the 0 state, it would flip it to the 1 state. If you applied a Hadamard gate, it would put it to an equal superposition on the equator of the block sphere, and that's shown here in the second figure. Okay. All right, and then finally, this notation here is when we have multiple qubits and we want to apply gates to them, we can represent them as quantum circuits. And that's the last piece of information we need before we talk about algorithms. And I'm just keeping an eye on the clock because I don't want to get too wrapped up here. But these are this is the way we represent the quantum circuits. We have these wires, which are not real wires, but they represent the path by which each of the qubits, this in case Q0, Q1, and Q2, go through. They initialize them here in the 0 state. Then they apply a Hadamard gate here to the 1 qubit, and then a controlled NOT gate to the 1 and 2 qubit, then a Hadamard gate to the, then a controlled NOT gate to the 0 and 1, another Hadamard, and then these are measurement operators where we actually check the state of the qubit, collapse the wave function, and probabilistically get an outcome from our circuit. And so this is typically the way quantum computing is both represented mathematically and graphically. Okay, The last slide on this crash course is quantum algorithms. You put a bunch of these circuits together, a bunch of these operations together, you create algorithms, and the idea is to solve problems of practical interest and ideally to do them much faster than what you could do classically. So one of my favorite algorithms, which I'm not an expert at all, but it was what I fell in love with quantum computing back in the 2010s, and that's the HHL algorithm, which is named after its authors, Harrow, Hasidim, and Lloyd. And it's a quantum algorithm for solving linear systems of algebraic equations, which everybody on this call knows and loves as a result of the need for doing this in CFD. So it actually solves a quantum linear system problem, which is A ket x equals ket b, which is a little bit different, but it's related. And the idea is if you could somehow invert the matrix, then you could pre-multiply it by the vector b, and then you would get the quantum state, which is the solution to the quantum linear system problem. This was first presented in a paper in 2009, and I found it the year later, and that's how I got started in this when I was back at Purdue. Here's an example for a 2x2 system with 4 qubits. You have 2 qubits here. You have an ancilla, which is like an assistant, a helper qubit, and then you have a memory qubit to store the right-hand side vector b. There are 3 phases to this algorithm without getting into the details, one called phase estimation, one called control rotation, and one called inverse phase estimation. And then the end, after you execute these 3 blocks of gates, will give you hopefully the answer to your problem. And the exciting part is that it potentially gives you an exponential speed up. The operational count is order log n, which is much better than Gauss elimination, much better than conjugate gradient method. It's a very potentially exciting algorithm for this problem. And there are a number of steps involved with encoding the B vector into a quantum state by amplitude encoding the A matrix into a unitary operator through what's called Hamiltonian encoding. And then the other thing is when you finally get the quantum state out, you actually want the amplitudes of the basis vectors here. That's the solution to your original problem, and that turns out to be computationally expensive and potentially could destroy the speed up that you got from getting the solution in the first place. This has been implemented a number of times over the years. This is an example of a quantum circuit that was done using IBM's API called Qiskit, which is an open source Python-based programming environment for quantum computing. And it's only been used so far to solve systems of 2x2 matrices up to 8x8 matrices, definitely not a DNS of turbulence anytime soon. And there are a number of caveats, as I mentioned already, with regard to input-output, both in terms of setting up the right-hand side vector B and getting the matrix, getting the solution out of the quantum state X. And this is not a NISQ-friendly algorithm. What I mean by NISQ, I'm going to be describing in a few minutes, but it cannot be implemented practically on today's quantum computers. They're too small, too few numbers of qubits, and too noisy, as we're going to discuss. But I just put a code snippet here. This is just typical Python. This is what you see in Qiskit, just so you know that the programming environment will feel very familiar to you from your normal everyday CFD work. Okay, so with that crash course, and I'm keeping an eye on the clock, I think we're good. Just one slide on what I know, which is very little. Like I said, I found this paper back in 2009, 2010 when I was at Purdue. I recruited a student, a very motivated, a bright student named Yudong Cao. I found a collaborator, Professor Sabre Kayas in chemistry, who knew something about quantum computing, and I said, let's do this, quantum CFD thing. And long story short is we ended up with a paper that has been nicely cited over the years. And Yudong, which is what I really care about is how my students do when they leave, went on to be the CTO and co-founder of Zapata Computing, which is one of the top startups in the world in quantum algorithms. So that was my first exposure. Then I left and moved to the Technion about 10 years ago. And it was in 2020, right around COVID time, that I took a sabbatical leave. And as Dipankar mentioned, I worked full-time at Quantum Machines, which was a startup in Israel at the time. And this is Yonatan Cohen, the CTO, who also was my boss. And it was a really great experience for me. I was able to write some proposals, get some funding, and now develop a program in this space. Okay, let's take a brief 2 minutes to breathe, because that was a lot of information, and I'm from New York and I talk fast, so I apologize. And I mentioned this is beyond the hype, so I wanted to expose you to a little bit of the hype in this space. As you know, there's a lot of hype on the internet about a lot of new technologies, including machine learning and AI, and quantum computing is no exception. So just a few words on that. The hype really started back in 2019 when I was actually starting my sabbatical with Google's claim of quantum supremacy. They were able to demonstrate with their 53 qubit, superconducting qubit processor called Sycamore. Here's a picture of the processor, and here's a picture of the dilution refrigerator surrounding it, that they were able to do execute a quantum circuit and make measurements in 200 seconds, where with a classical computer it would take 10,000 years. I'm not exactly sure how they estimate that, but they claimed quantum supremacy, and they made the cover of Nature. A few months later, the Chinese came out with something very similar. And then just recently in 2023, earlier a couple months ago, IBM came out with a little more modest claim of quantum utility, which is a different way of saying we can do something on a quantum computer that's useful and it's not possible or can't be done efficiently on a classical computer. And they had to use quantum error mitigation to do this, and we'll talk about that briefly in a few minutes. But they used their recent 127 superconducting qubit processor called Eagle, which is shown here, and the dilution fridge is shown here. So this is some of the early claims for, between Google and IBM, supremacy versus utility. But very quickly after that, and it was fascinating, within 2 weeks of the paper appearing, there were tweets coming out. It says, remember the recent New York Times headline about IBM quantum experiment that started a new era? He says, well, that era lasted for less than 2 weeks, since the experiment had just been simulated classically. So what they said they did on their 127 quantum computer was able to be done in a couple of weeks' time on a classical computer. So that kind of, in some sense took the air out of their announcement, but it's not a problem. But then there were more. So here's the paper that they cited. This is the abstract from the archive. Then in August 6th, so just a couple weeks ago, another experiment was done, repeating their experiment classically. And then just August 17th, so last week or a couple days ago, this paper came out where they did the same thing. It says, by now, the recent IBM experiment has been simulated so many times that it's become a benchmark for new classical simulation algorithms. So it's very humorous to follow this. And of course, Twitter results in Twitter wars. And this was Jay Gambetta from IBM. He's the head of IBM Quantum there, basically defending their paper and supporting these additional efforts on to reproduce their experiment. And then there's some back and forth. He's holding IBM to a very high standard here. The paper has lost IBM a lot of respect. He says this is disappointing. So it's a heated space right now, which is exciting. It's exciting. But basically, Kristen Tem, who's one of the top guys at IBM, who was in Israel just a month or two ago, I got to meet him. He said the crux of the work is that we can now use all 127 of Eagle's qubits to run a pretty sizable and deep circuit, and the numbers come out correct. So this is definitely a big accomplishment. Speaking of hype, there was a great book that came out earlier this year called Quantum Supremacy by Michio Kaku, who's a world-renowned physicist, string theory person. I was so excited. I bought the book. I started reading it. But then I saw a review by Scott Aronson, who's one of the top computer scientists in the world in the quantum computing space, and he said that the book is the worst book about quantum computing he's ever saw. So I actually got to meet him in June in Jerusalem at a conference that was held there. I told him he owes me $14.99 for the book that I bought because he ruined it for me with his comment. But anyway, okay. And this was some hype that came out this summer, which I think is of interest to this group here. NVIDIA, Rolls-Royce, and Classic, this is an Israeli startup company that I know, announced quantum computing breakthrough for CFD in jet engines, world's largest quantum circuit for industrial simulation to advance development of quantum computing in aerospace. Sounds great, and they even put a picture of a jet engine in the write-up. But at the end of the day, it was probably a lid-driven cavity problem. And what they did is they solved AX equals B using some version of HHL with 39 qubits, 10 million layers, but they did it on a GPU. It wasn't done on a quantum computer. It was done on a simulator, which is a classical computer that basically does the matrix vector products that implement the circuits, to emulate what a quantum computer would do. So you have to be very careful when you read these hype presentations. And then more Google hype in July. The supercomputer the quantum computer makes calculations in the blink of an eye, which I checked is 6 seconds, they said, that takes rivals 47 years. So again, there's a lot of these headlines and there's a lot of hype. So, okay, so what can we actually do with today's quantum computer anyway, right? It's one of my favorite comics that's been floating around the internet for years, but you can read it and chuckle before I go to the next slide. Now you already know something, a little bit about quantum computing. You probably can understand the jokes here. Okay, so continue our quantum computing crash course, but bringing us up to present day. So we are currently in what's called the NISQ era of quantum computing. NISQ stands for Noisy Intermediate Scale Quantum Computing, which just means tens of qubits and they're noisy. It's like on your laptop, you keep hitting the J, every once in a while you get a K. It's like it makes mistakes, okay? So, what can we do with small numbers of noisy qubits? Should we just wait until we get out into the, millions of perfect qubits, which could be 5 years, could be 10 years, could be 20 years from now? Or should we try and do something with these NISQ machines? The sources of noise are just basically interactions with the environment that tend to take the qubit out of its quantum state, whether that's a superposition or a certain phase. It just starts to lose its coherence, so to speak, due to the noise. So this is a typical quantum circuit, with the circuit width being defined as the number of qubits in the vertical, and the circuit depth being the number of layers of gates that are applied to the qubit. And in the NISQ era, you basically have narrow and shallow circuits. You can't have that. You don't have that many qubits, okay? And you can't have that large a circuit depth, because by the time you get to these layers here, the qubit has already lost its coherence and you're getting garbage as your calculation. So you need short, narrow circuits. So what do you do? So what people have come up with is the idea of hybrid quantum classical computing, where you use the limited capabilities of the NISQ quantum computer to do what it does best, which is perhaps represent large spaces of your solution, and perhaps implement certain types of algorithms. And then you use a classical computer to do what it does best, and they work hand in hand in a feedback loop. And this has resulted in a class of algorithms called variational quantum algorithms, or VQAs. And this is a generic schematic of a VQA, where you've got a set of qubits, let's say initially in the 0 state. You apply a series of gates, and each of the gates are parameterized by the gate angle. So these phi's here are the angles of the rotation on the Bloch sphere, if you will, that you're going to be subjecting the qubits to, and those are parameterized. So they're initially, let's say, chosen as random, but we're going to learn those parameters much in the way we learn the weights of a neural network in a machine learning algorithm in this overall algorithmic loop. So we apply this parameterized quantum circuit, a series of quantum gates with parameterized angles. We make a series of measurements. We do some post-processing to compute a cost function, which is a function of the parameter vector phi. And then we take that cost function and we do a classical optimization, a gradient-based or non-gradient-based optimization, typically what they do in machine learning. And we update the parameters. And then we take those new updated parameters, we reinitialize the circuit, apply the parameterized quantum circuit again, and repeat. And ideally, this converges and you get the optimal parameters for your problem. And that will then solve what this cost function is represented, whether it's AX equals B or some other physics or chemistry type problem that you're trying to solve. Okay, these have been used in a number of different applications, or at least they've been envisioned to be used in a number of different applications. There's a great review article here that you can check out, and this is the figure from that review article showing you finding ground states, for example, of in quantum chemistry or condensed matter materials, machine learning, optimization, solving systems of equations, factoring, a lot of different application areas for VQAs. At the highest level, a VQA, like I said, is a hybrid quantum classical algorithm. And the prototypical, the original VQA, which came out in 2014, is called the variational quantum eigensolver, which, as the name suggests, it determines the eigenvalues of a matrix. And it was developed originally and is mostly used for finding the ground state of a Hamiltonian. A Hamiltonian is a function that describes the energy state of your material, whether it's a molecule or a piece of metal or something like that. So quantum chemistry and materials processing is where this comes into play. And again, you encode the energy state of the molecule, let's say the Hamiltonian, into the quantum computer. You prepare the state, you make the measurements, you send the cost function, which is basically the Hamiltonian, the average of the Hamiltonian, to the classical computer, update the parameters, repeat, and when you're done, you'll predict the ground state, for example, of the molecule's energy as a function of, let's say, the internuclear distance between the nuclei or the atoms of the molecule that you're considering. So this is what we started with a year or so ago, and this is our schematic now of a VQE. And there to help you understand the process, there are 4 major steps. I came up with this acronym called GAMCO, which is a gate-based ansatz. The ansatz is another name for the parameterized quantum circuit because it's really a variational estimate of the solution to your problem, right? You don't know what the right parameters are, but through this optimization, you're going to find them, and this is going to be your solution. So this is your ansatz, your guess. If it's a gate-based ansatz, which is what they typically are, we call it a gansatz. As I'm going to explain why we call it that in just a minute. So we apply the gansatz, we make the measurements over here, we compute the cost function, we send it to the classical optimizer, and we update the parameters and repeat. So this is a typical VQE, it's a VQA, but it's specifically the VQE, the variational quantum eigensolver, with gate-based ansatz. There was a paper that came out in 2021 while I was on my sabbatical that really inspired me. It was something called Pulses to Circuits and Back Again. What you should understand is that when you take a typical quantum circuit, like shown here, we have 2 qubits and a series of gates. At the hardware level, through compilation and transpilation of these gates, a gate, for example, an RX gate, an X gate in an IBM quantum computer is actually translated into a series of 4 gates, a square root of X gate, an RZ gate, another square root of X gate, and another RZ gate. So, and then these individual gates at the hardware level are translated into electromagnetic pulses. These may be microwaves applied to the superconducting circuit. They may be lasers applied to the trapped ions, or they may be, photons applied to a light-based quantum computer. But at the end of the day, these electromagnetic pulses are what make the change of state in the qubit. So the gates are obviously abstractions at the highest level. And because one gate translates into 4 here, the noise is 4 times as much as if you had a single gate. And so the idea was, people have looked at this in the past, to optimize these pulses using standard optimization approaches to maximize the fidelity of a gate operation. But we had this idea of combining the optimization of pulses with the VQA. So our idea was, and this is the only novel idea I've had in the space so far, is to replace the parameterized gates that I talked about with parameterized pulses. And we asked the question, what if VQAs optimize parameterized pulses directly rather than parameterized gates as part of the cost function minimization process? We would basically be bypassing the gates almost entirely. And we hypothesized that this would result in shorter circuit durations and more accurate results, less noise. So in a nutshell, if this is a typical VQE or VQA, we would replace this box, which are parameterized gates, with parameterized pulses. Okay, and we would learn the parameters of the pulse as part of the overall optimization. So that's what we did. And we came up with something called a pulse-based ansatz, which I called PONSATz, which I kind of like. And that's why I called the gate-based ansatz GANSATz. Okay, I got to keep an eye on the clock here. So here's the same exact schematic that you saw before, except if you compare, instead of the gate-based ansatz, we have these pulses. And what we're learning, the parameters of the pulses that we're learning are the pulse duration. We're fixing the shapes of the pulses, the amplitudes of the pulses, but we're allowing the pulse duration, how long the pulse is applied in nanoseconds or whatever, to be a parameter. And we're going to learn that as part of the optimization process. And this worked. And we put a paper on the archive. You can get the link here. And these are some results from running on an actual quantum computer. We ran on the IBM Q quantum computer system that they have, a device called Lagos. And what we're showing here is the energy versus atomic distance for a hydrogen molecule. So it's got 2 atoms here, 2 hydrogen atoms. And we're showing that we can get very accurate results compared to the exact solution, so to speak, which is the blue curve with our approach. But more importantly, on the right, we have the circuit duration. So for the gate-based, the circuit duration for all the interatomic distances is roughly north of 350 nanoseconds. But with our pulse-based approach, we're down here below 50 nanoseconds and at the maximum 150 nanoseconds, a considerable savings in circuit duration, and that translates into less noise, more accurate results, and potentially larger molecules that can now be tackled with this approach. Okay, so with that, let's now turn to quantum CFD, and with two pieces of the talk here. I'll try and do 5 minutes each on them if that's possible. And the first one is based on AX equals B, right? So in a nutshell, here is my view of the quantum CFD space as it's appeared in the last year or so in publication. So you can always take your CFD problem and apply a traditional discretization like a finite volume, finite element, finite difference, and produce a linear system of algebraic equations. Then you can turn to HHL, which offers potentially an exponential speed up, the best possible speed up you can get on a quantum computer. Here's the algorithm as we saw before. The only problem is it's not NISQ friendly. It cannot be implemented. You saw we only solved 2x2, 8x8 systems with HHL. It's not ready for a billion grid points at any time soon. But there was a recent development, again, while I was on my sabbatical, which was a variational quantum algorithm, a VQA, for solving linear systems. And it's called the Variational Quantum Linear Solver, VQLS. And this is the schematic. We'll talk about it in just a minute. So this is one of the first options that we're going to talk about in the next slide. Here you can come up with totally new algorithms. So Frank Gatan, who I was in touch with during my sabbatical, came up with something where basically he took the compressible Euler equations, did a semi-discrete approach to discretize the spatial derivatives, left the time derivative intact, and basically had a large system of nonlinear ODEs. And he used something called quantum amplitude estimation algorithm to implement that on a quantum computer. Of course, he didn't really do it on a quantum computer, and you really can't because, again, it's not a NISQ-friendly algorithm. But again, he had the words Navier-Stokes and quantum computing in the title, and it brought a lot of people's attention to the field. Another alternative, which we'll talk about briefly in a few minutes, is the quantum lattice Boltzmann method. And this was been pioneered by Budinsky and Stelja and Suchi, who's the godfather of quantum computing, and of lattice Boltzmann, excuse me. And we'll talk about this briefly as well. The last one is something called Hamiltonian simulation, which is a way to basically transform the Navier-Stokes equations into the Schrodinger equations, because when the qubits evolve on a quantum computer, they follow the Schrodinger equation. So if we can somehow transform the Navier-Stokes equations into the Schrodinger equation, we can allow this to evolve on a quantum computer and hopefully solve the Navier-Stokes equations as a result. So there's something called the Schrodingerization of the Navier-Stokes equations. There's something called the hydrodynamic Schrodinger equation. And then finally, there's the quantum simulations of hydrodynamics via the Madelung transformation, which is a transformation that goes back a long time ago to relate the Navier-Stokes equations to the Schrodinger equations. So these are, in a quick nutshell, the approaches that are out there now. Okay, so quantum CFD, variational quantum linear system solver. Now this one has been used by Bravo Pietro in his PhD thesis. He used 10 qubits. He actually ran it on Righetti's superconducting quantum computer, and he solved a 1024 by 1024 matrix system, much larger than 2x2 and 8x8, right? And in this case here, there's some details, technical details, which I won't get into right now because of time, but at the end of the day, there's a cost function that we want to minimize to solve the AX equals B problem, okay? And here is the schematic of the algorithm. Again, the quantum computer, here's the ansatz. This V of alpha is the ansatz. So you take the zero state, you apply a parameterized quantum circuit. That becomes your initial guess for your solution X. That's done here. You've got your implementation of your A matrix through unitary representation that's shown here, you run this quantum computer, you compute a cost function as a function of these parameters alpha, you run a classical optimization on a GPU or whatever, and you update the parameters alpha. If you haven't converged, you send the new parameters back, rerun the quantum circuit, and repeat. And eventually you'll get the optimal parameters, which you plug into the circuit, and then you can compute the quantum solution to your problem. Okay, and this has already been implemented in Qiskit. You can click on this link and see the code and run it yourself, either in a simulation or on actual hardware. A couple of recent papers have implemented this in the context that you and I are all familiar with. Here's a VQLS for a 2D steady heat equation. Now, this is something we can all understand. So we took a Laplace equation, a 5-point finite difference approximation resulting in a pentadiagonal matrix. VQLS schematic here, 8 qubits allowing 16 by 16 grid, which is, again, not that exciting, but it's something, and getting good solutions and discussing pros and cons as a result. And then more recently in 2023, VQLS for the finite element method, again, something a commercial CFD company is probably familiar with. They did a Poisson equation in 1D, a heat equation in 1D, and a wave equation in 1D. And basically what they did is with the finite element method, you get the weak form of the equation and you get a stiffness matrix type system of equations to solve both steady and unsteady problems. They implemented this in a simulation and got results and discussed the pros and cons there. And you can see the paper for more. What we're trying to do is solve the compressible Navier-Stokes equations, because right now we're interested in high-speed flows. And here's the compressible Navier-Stokes equations in vector form that we're all familiar with. And what you see in these equations is derivatives everywhere, right? We need to discretize derivatives everywhere. So our approach right now is to take a simplified form of the Navier-Stokes equations, like the advection equation here. And if f is equal to u squared, this is the Burger's equation. If it's linear, it's the advection equation. We discretize it on a grid. We can approximate the derivative df dx either explicitly using any of our favorite finite difference formulas. Here's a center difference representation, or implicitly using a compact finite difference approximation, which we know from CFD has much better spectral properties, which are very important, by the way, in CFD, as you probably know. And then as a result, this gives us a system of linear algebraic equations, happens to be tridiagonal, that we can then solve using a quantum algorithm. So the idea that we're pursuing is, here's our advection equation, here's our our compact finite difference representation of the derivative, here's our resulting matrix system shown here to solve for the derivatives, here's our VQLS. Once we get that derivative, it's going to be a quantum state. We have to worry about how to get that into a classical state, and then we could update our solution and march in time. So this is what we're envisioning right now, and we're working on this as we speak. This is just a couple slides illustrating some of the details that my student was working on over the summer. Just to let you know that we are working on this. We are writing code. Here's some code here to build an ansatz. So we're starting with the gate-based approach, but our ultimate goal is to use our Ponsatz approach, our pulse-based approach, and hopefully get a better result. So it's a work in progress here. Finally, quantum LBM. I'll just take a few more minutes and we'll finish for questions. So lattice-Boltzmann method is an alternative way of doing CFD. Instead of solving the Navier-Stokes equations, we solve the lattice-Boltzmann equation for the particle distribution function f. There are two operations that we have to implement. One is streaming, which is a non-local operation in terms of the lattice grid, but it's linear, and a non-linear but local operation called the collision operator, which models diffusion, relaxation to equilibrium, shown here. And so these operations are very well familiar with classical lattice-Boltzmann implementations. You can write a short Python code and do this movie in about a half hour. These are the steps involved in the lattice-Boltzmann method. These are some of the lattices that you can choose depending on whether you're 1D, 2D, 3D, or higher order or lower order, and this can be implemented directly. But what about quantum lattice-Boltzmann? So this is what's been done in the last year on quantum lattice-Boltzmann. I mentioned Budinsky earlier. He's tackling the advection diffusion equation and deriving quantum circuits and algorithms for implementing lattice-Boltzmann and getting results. Again, not NISQ friendly, so great for publications, but not for practical application. Itani and Suchi are doing some very nice work using something called Kalman linearization, which goes back to the 1920s. It's a technique to take a finite dimensional nonlinear system and convert it into an infinite dimensional linear system, then truncate that infinite dimensional system and solve the linear system. And then there was another approach recently where they were doing another approach to implementing a one-dimensional quantum lattice-Boltzmann method. There are some papers recently that have appeared looking at the potential quantum advantage. They say that exponential quantum advantage may exist. Of course, it may not exist. That's the danger of saying may for simulating fluid dynamics. So you can check this paper out and read about the use of Kalman linearization there. Here's Lubinsky's blog post back in March, where they're, I guess, on the verge of releasing commercial software to do this with the Quantian company. I'm not sure how useful that is, but that's what they're working on. And then in May, there was another very nice paper dealing with an implementation and including Burger's equation, which is, of course, very important for eventually simulating turbulence. Okay, so what are we doing? We're trying to come up with a NISQ-friendly variational quantum algorithm. So we want a variational quantum lattice-Boltzmann method. So what we're pursuing is, we recognize that the streaming operator and the collision operator can be represented in matrix vector products. And we can use a variational quantum algorithm to implement those matrix vector products. So in this slide, we're using the VQE method to do this matrix vector multiplication by forming defining the ground state of this Hamiltonian, which will give us the solution to this matrix vector product. So this is brand new stuff we're working on. Please don't share this with your friends. We haven't published it yet, but we're working on this now. And then another approach, you can also represent the streaming matrix and collision matrix as a linear system solve. By cleverly rearranging the equation, you can actually get an AX equals B system here. And then you can do it for both streaming and collision, and you can call VQLS to solve that system on a quantum computer directly. So this is what we're pursuing right now in our lab. Again, work in progress. Okay, so to summarize in the last minute before our 10-minute question and discussion session, we talked a lot about quantum computing and NISQ. We basically have few qubits, shallow depth circuits. Quantum error mitigation, which I didn't talk about, is all the rage right now. This is basically Richardson extrapolation for quantum computing, where we run the circuit by deliberately increasing the noise level, and then we take multiple solutions and extrapolate using Richardson extrapolation to zero noise. So this is what IBM is doing in their quantum utility paper. VQAs are the state of the art in algorithms. Variational quantum eigensolver is for finding the ground state of Hamiltonians. QAOA is for combinatorial optimization problems, very popular in the finance and other non-science and engineering fields. VQLS for solving linear systems. For quantum CFD, one approach, discretize an Navier-Stokes equation, solve X equals B on a quantum computer using VQLS. Other approaches like quantum lattice Boltzmann, Hamiltonian simulation, and other approaches soon to be discovered can be pursued. Our results, not quite jet engines, not even quite CFD, but we're looking at VQLS to implement a quantum compact finite difference derivative subroutine, VQE and VQLS for a NISQ-friendly LBM. We're taking two approaches here. We're looking at this from the bottom up, trying to build small programs, 1D programs to do this, but we're also looking at it from the top down, taking one of our state-of-the-art GPU accelerated CFD codes and trying to peel off a subroutine of that and create a quantum subroutine that can help accelerate, just like we do with GPU acceleration, we can have QPU acceleration as well. If you want to learn more, I highly recommend the Qiskit website. They have an online textbook where you can actually run Jupyter notebooks and do a lot of this stuff. There's two great textbooks. This one's free. This one's from Springer. You can get it online, and I highly recommend these. Again, I'll share the slides so you'll have the links later on. And thank you for coming beyond the hype, and I'd be happy to try and answer any questions that you may have.
Thank you, Professor Frankel. That's fantastic. I mean, you've managed to pack
Or
a
a train
lot
wreck,
into
one or the other.
50 minutes. No. I mean, you can see from the appreciation from the audience. Can you see those virtual thumbs up?
Oh, thank you so much. Wow,
yeah,
no, you guys are the best.
It's truly appreciated.
To be able to speak to you.
Yeah. So if you, I'll pose a few of the common questions that came in through chat, but also a few of the attendees have mic privileges, like Vincent Martin and Bob Lucas. There are two people who work in this field within ANSYS. Vincent or Bob, do you have any questions? Just unmute yourself and ask your questions, and then I'll turn it over to the chat questions.
Vincent, do you hear me?
Yes. Go ahead, Vincent.
Vincent Martin. I don't have any particular question because the talk was quite clear, to be honest, and very good sum up of all the techniques I know of and some I didn't know of. I'm more prone on lattice Boltzmann methods for the moment. But the VQLS applications to CFD I didn't hear about, and this is very interesting. And my question is maybe, well, of course you're a bit biased because this is your method, but do you think, what are the advantages, I'd say, of the VQLS method compared to the lattice Boltzmann method for CFD?
Yeah, so thanks for the question, Vincent, and I'm glad you said you thought the talk was clear. I thought you were going to say it's not clear, so I don't have any questions. I didn't understand anything. But no, the VQLS, first of all, is not ours. We didn't develop it. What we developed is this pulse-based approach, which we hope will improve the accuracy and efficiency of VQLS. But the main difference is that with VQLS, you can stick with your traditional CFD discretization techniques and just take advantage of the quantum computer to solve the linear system of algebraic equations, which you know is the real workhorse behind a lot of CFD algorithms. Whereas lattice Boltzmann is a totally different approach. And like I said, none of the approaches that we've seen in lattice Boltzmann are NISQ friendly, which is fine. You can aim for the future. Within the next 5-10 years, hopefully we'll have larger fault tolerant quantum computers, and maybe you'll be the first out of the box to have a working code. But in my lab, we try and hit the highest fidelity with the highest impact today. So we're going with, well, we're going with both because we don't want to put all our eggs in one basket. So I have two students that are working on these topics separately and together, because you can see in our idea for quantum lattice Boltzmann, we're going to use VQLS to implement the streaming and collision operator. So that's something that we there was a quote-unquote novel idea. It's a simple idea, actually, but we don't know if it's going to work yet. We're coding as we speak, and I was hoping to have something to show you, but it doesn't work out that way. So that's the main difference, though, Vincent, is that with the VQLS, you can stick with your traditional discretization techniques, whereas quantum LBM is obviously only for LBM approaches.
Okay, thank you. And the fact that it is not NIST-friendly is also quite a bummer. Okay, well, thank you. That was my main interrogation, I'd say, from your presentation.
Thank you so much, Vincent. Thank you.
Thank you, Vincent. So I'm going to just turn to the chat windows, Stephen. So I'm just going by order here. So one question is from Micah, since the parameter phi is the rotation on the block sphere of your qubit, and you apply these rotations using gates, is the classical system essentially optimizing how you apply the gates?
Yes, it is. So you know what you're doing is you have this parameterized quantum circuit, which is also called an ansatz. Just like in a variational approach, like in finite element methods or spectral methods, you have a variational, you know, trial solution, right? And you're gonna solve for the coefficients as a result of your implementation of your Galerkin method or whatever it is. Here, the parameterized circuit serves as your ansatz, your guess for your solution, and you're going to learn the parameters, which are the angles of these gates, through a machine learning. It's also called a quantum neural network, by the way. People refer to it as quantum machine learning. It's the same idea. You're just like you learn the weights and biases of a neural network through optimization by minimizing a cost function. You're doing the same thing here, except instead of a neural network, you're a series of quantum gates that are parameterized by their angles, and that's basically the main difference there.
Okay.
Yeah.
And then Mike also asks, with respect to the GAN-SATs versus BAN-SATs, weren't the pulses the physical mechanism being used to apply gates? So how is optimizing the pulses distinct or different from optimizing the gates? I don't know if you got the question there.
Yeah, no, I understand the question. So from what I understand with quantum computer hardware is, first of all, we all recognize these gates are abstractions. This is the way we implement changes to the quantum state of the qubit to do some computation. And the gates are eventually compiled and then transpiled down to electromagnetic pulses at the hardware level. There's a microwave signal that comes in that zaps the qubit to change it from the 0 to the 1 state or whatever you're trying to do. And that is an electromagnetic pulse. It has some sort of a shape, and it is optimized to increase the fidelity of the gate operation. So if I want to implement an X gate and I want to change from a 0 to a 1 state, I want that to happen with 100% fidelity. Right now, it's not exactly 100%. It's like 0.99 something or whatever. But they optimize those pulses a priori. In fact, every day they calibrate them in order to optimize these gates. But because of the waste and the additional overhead of translating these gates into multiple gates, we said, you know what? If you're going to optimize the pulses, instead of optimizing them a priori, optimize them as part of the overall variational quantum optimization process. You know, we don't want to pre-wire the pulses and then, you know, have this overhead of these extra gates. So it's a way to bypass the gates and result in even more optimal pulses to solve your problem, which at the end of the day is what you really care about.
Yeah, got it. In fact, Vincent Martin, the gentleman who asked you the question on the mic, he's been answering some of the questions along the way in the chat. So he's sort of been an assistant in this process.
Thank you.
So
the check is in the mail.
Okay. All right. So now let me just look at. There's one question early on which said, "Hi, Professor Frankel. Thanks for this talk. Whenever I see error correction, I would typically think of Hamming codes. Assuming this approach has already been tried and tested, where does this technique break down?" I don't know anything about the question.
No problem. So what I think is being referred to here is what's called quantum error correction, which has been, you know, theoretically known for many years that in order to protect these quantum states and to these quantum operations and to minimize the error, we would need to do quantum error correction. And that's typically done as similar to error correction on classical computers with redundancy, building redundancy. So instead of to get one accurate physical qubit, you may need multiple logical qubits to duplicate the state so that you can correct errors. And that's a very active area of research. It is going to be necessary for fault-tolerant quantum computers if you really want to make sure you don't have any errors. But right now, what's being done on the NISQ computers is what's called quantum error mitigation. It's along the same lines. You want to reduce error, but it's not quantum error correction. So these Hamming codes and these surface codes and some of these other things that are out there, they're actively being worked on by all the big quantum computing companies for eventual use in fault-tolerant quantum computers. But as of now, right now, quantum error mitigation, which, as I said, it's like Richardson extrapolation. You run one calculation with one error, then you deliberately increase the error, run multiple calculations, and then take those results and extrapolate down to zero noise. So that's yeah. Sorry if that's not clear.
Thank you. Just one or two more questions, Professor Frankel. I know it's already late for you, so
no, it's fine.
Giving us the time.
Happy
So more Metabody asks, with quantum computing, is the notion of serial and parallel computing a relevant thing anymore?
That's a great question, really great question. So first of all, there's something called quantum parallelism in and of itself. If you have a quantum computer, just a single computer, not multiple computers, and you have multiple qubits, each qubit, as I said, can be in a superposition of two states. So when you think about a standard bit, it's either 0 or 1. If you want to evaluate f of x, you can put in x and you get back f. But with a qubit, you put in the qubit and you evaluate the function, you get 2 for the price of 1. So that's called quantum parallelism, and that's one of the power of superposition in enabling, advanced, more powerful quantum computing. In terms of the traditional idea of serial versus parallel, there are companies working on taking multiple quantum computers and networking them together. But I think at this point, it's just a little bit premature because getting just one quantum computer to work well is a challenge. So I think at some point, MPI and all this other stuff might come into play. But yeah, it's right now, it's in the early stages. So
okay.
Yeah.
Okay. I'm skipping over a few questions that Vincent has already responded to.
People can email me if they like, afterwards. I'll be happy to correspond if I can help.
Fantastic. Then I'll just pose just one more question. This is from my namesake, Dipankar Pal. Do you have any publicly available Q finite element GitHub directory? And then his follow-up question is, what do you think about Yamamoto's work with respect to finite elements? He might be referring to a particular train of investigation.
Yeah, I don't know the paper off the top of my head. If he wants to send me a link, I could take a look. Maybe it's one of the ones that I already cited. I don't know. In terms of a public available repository, we did create we haven't shared it yet, but we did create a GitHub for the Ponsatz approach. Because it's not easy to build. My student actually works for IBM, so he had some experience with this, and he built it out for us. So the paper is being reviewed for publication right now, and we would be happy to release the GitHub for that. In terms of a quantum finite element method, there are some GitHub repositories already out there. If you are good at Google skills, you could probably find them. I could ask one of my students to give us a couple links. But as we start to develop these codes, once we're able to solve a PDE, for example, yeah, we'll definitely open source those because, this is not, top secret stuff. It's just basically, fundamental building blocks. But at the moment, we don't have anything out there to share. So the paper is available, but yeah.
So Dipankar and others, please feel free to connect up with Professor Frankel and, give him the specific citation you're referring to. And this is truly the last question, Professor Frankel.
I'm enjoying it.
We've used your time enough here. This is from Polisu. Thank you, Professor Frankel. How do you guess a good ansatz? Is there a rule of thumb for that?
It's a great question. So first of all, within the context of gate-based ansatz, which is what the majority of quantum computing researchers use, there are two main types of ansatz. So what is the ansatz? It's basically your initial guess. So you'd like it to be close to the solution that you're looking for, right? So that you make the optimization process more convenient and you'll converge more quickly, right? It'll save computational time and resources. So you'd like the ansatz to be as close to the physical problem you're trying to solve as possible. So they're what are called physical-based ansatz, which are, if you know something about the physics of your problem you're solving, you can design these ansatz to be close to what you think the solution is supposed to be. And then there are what are called hardware-efficient ansatz, because while you may have a physics-based ansatz, to implement it on the particular hardware that you're using and the gate set that the vendor is providing, it may not be so easy to do. So a hardware-efficient ansatz takes advantage of the gate sets that are available on the particular computer that you're using, and you build your ansatz that way. But this is a great question because there's something called, and you've probably seen this in machine learning, called the barren plateau problem, where basically the cost function landscape has these zero gradient regions and the optimization stalls. And part of this is due to the choice of the ansatz. So there's a lot of papers on adaptive ansatz, adding layers of gates, removing layers of gates, doing all kinds of different things to try and improve the performance of the algorithm. So the choice of the ansatz, as your colleague just mentioned, is extremely important, and there are plenty of papers on that. I can point them to some if you want to email me. But yeah, for sure, it's important. And when you go to the pulse-based level, it's a little bit more abstract. You have to kind of know what you're doing, and that's where my student was able to put that together. But yeah, it's an open question right now what the optimal form of the ansatz is.
Fantastic. Well, thank you very much, Professor Frankel. This was, I think, really eye-opening for a lot of us and very educational. And fantastic. Thanks again, and thanks to the audience as well. We managed to hang on to nearly 200 people at the end, which is fantastic.
Wow, that's incredible. Thank you so much. It's an honor to me. Yeah, I'll work on posting the slides. I'll put together a PDF and send it over as soon as I can. Okay.
Thank you. Thanks.
Thank you very much for your attention and time. I appreciate it. We'll be in touch.
Likewise. Thank you.